So first of all, I want to welcome you today to our Risk Retirement Habitat Change Expert Forum. My name is Michaela Freeman, and we are very excited to have you join us today. I'm here presenting with my colleagues, Andrea Copping, Linang Hemery, and Deborah Rose, who you'll all hear from today. So on the agenda for today, some quick intros that we just did. Then I will be talking in the next several slides about risk retirement and data transferability. After that, we'll talk through habitat change, giving an overview of the different areas of habitat change we'll be discussing, as well as presenting the evidence base that we've compiled. After that, we'll have some case studies presented, one for Scotland and one for Oregon. Those will be followed by breakout groups where we'll have about 40 to 45 minutes for some discussion. We have some guided questions for those, and we really hope to get your feedback on the risk retirement process and if we can retire habitat change. And then we will follow up the breakout groups with a report out from each group, and then end the expert forum today with some next steps. So I'm going to start off by talking a little bit about risk retirement to make sure that we give you guys a good understanding of what we mean by risk retirement, as well as data transferability. So we're all starting with the same understanding as we go into our discussions later on today. So risk retirement has been used in the industry, but has really had no definition. What we mean by risk retirement is that for certain interactions, potential risks need not be fully investigated for every project. And what we're really talking about here are small developments of 1 to 2 devices. We aim to decrease the data collection burden on developers and decrease uncertainty by relying on what is already known and the availability of similar or suitable data from consented projects, from research projects, and from analogous industries. By doing so, we think potential risk can be retired for these small installations. It is important to note 2 things. One is that a retired risk can be re-examined in the future as more information becomes available. Specifically, as the industry moves towards larger arrays, there's likely a need to re-examine the effects. And 2, that this doesn't change or replace any regulatory process, but instead focused on making information more readily available and aiding those processes. So far we've looked at interactions we believe to have minimal risk, gathered together an evidence base for those potential risks, and described how the information can be applied to new projects. Through a series of workshops and expert consultations, we've considered underwater noise and electromagnetic fields, or EMF, likely ready for risk retirement for small numbers of devices. So this essentially means that if a developer were to put forth a proposal in an appropriate location for 1 to 2 devices, perhaps there does not need to be a great deal of monitoring for underwater noise and EMF. There are, of course, certain caveats, such as the need to know what the sound output from new types of devices are. But overall, this is really an attempt to move towards doing things in a more standard manner so that each study doesn't need to be redone at every new site and new MRA deployment. Next slide. So we developed a risk retirement pathway, which is shown here, to assess this ability to retire risks for marine renewable energy projects, and which leverages what is already known and available to streamline consenting processes. We really aim to develop a systematic process that allows you to gather the information needed to consent a project and assess the potential impact, analyze the information, and determine if there is risk. And we have presented this risk retirement pathway through conference workshops, online webinars to regulators, gotten feedback, and it's really been an iterative process developing it. So I'm going to walk through the different steps. First, we're going to start with the circles on the left here. So when regulators receive an applications for MRA developments, it's important to have a good project description. So this pathway starts here with describing the project or stressors, such as how many devices, what types of device, and how will they operate. It's also important to describe the marine animals, habitats, and uses of the oceans or receptors that occur in the same area. And then we enter into the pathway with a series of stage gates. With the information of stressors and receptors, it's possible to define the potential risk of the project. Is there something about the device that might cause harm to the defined receptors? If you determine that there is not a plausible risk in this stage gate 1, there's an off-ramp shown with the down arrow. that denotes that the particular risk for that situation can be retired. However, if there is a reasonable risk, you go on to stage gate 2. Here you examine existing data and assess if the data provides enough information to determine if the risk is no longer a concern. If that's the case, there's another off-ramp and you would consider it to be retired. However, if sufficient data is not available or uncertainties remain, you move into stage gate 3. Here, it's important for the applicant, in conjunction with the regulator, to develop a monitoring program and collect data to better examine and understand a potential risk to see if it is acceptable. Once the data has been collected and examined, and if there's still a risk, you will have to move on to stage gate 4. At this point, mitigation is likely needed, and it's important to determine if there are existing mitigation measures that are adequate and have been tested and shown to be effective. If this is the case, you can mitigate the risk and take the off-ramp below. However, if there aren't adequate mitigation measures, you move on to stage gate 5, where it might be necessary to develop and test novel mitigation measures that could be effective. If these new measures are effective, you can retire the risk. However, if this isn't adequate, you continue down the pathway. At this point, if the risk is significant and cannot be mitigated, it's important to consider redesigning the project, moving to another more suitable location, or even abandoning the project altogether. So in this process, having access to relevant data and information is extremely important. We developed a data transferability process, which I'll go into in additional detail in the next 2 slides. But I wanted to point out here that data transferability is a key component in moving towards risk retirement, and specifically in stage gate 2. So for example, if sufficient data doesn't exist for the specific location or project, the data transferability process could be employed to investigate if sufficient data exists from another site or an analogous industry and can inform risk retirement for the project in question. I also want to note that at the top there are dotted lines and arrows, which implies that there are feedback loops between and among the different stage gates in this pathway. Next slide, please. So I also want to, as I mentioned, define data transferability, as this is a key part of the process. So by engaging with the international marine renewable energy community through online webinars, conference workshops, and a regulator survey, it really became apparent that there was a need for sharing data between marine renewable energy projects to help advance the industry. We believe that data and information collected through research studies and monitoring from other projects should inform new projects. And in addition, data and information from analogous industries may be able to inform new MRE projects when impacts or effects are similar and comparable. We do recognize that some site-specific data will be needed for all new projects, but that existing data should be used as much as possible, and data transfer can reduce some of those site-specific needs. By data, this can include raw or quality controlled data, but more likely it will come in the form of analyzed or synthesized data, information, or reports. And it is important to note that data that might be transferred should be collected consistently to allow for comparison. So in order to systematically evaluate data sets to be transferred and bring them into consenting processes that are moving forward now, we developed a data transferability process shown by the figure here. I'm not going to go into too much detail, but I just want to run through what's included in the process, which is a framework as the focal point, a data collection consistency table, monitoring data sets discoverability matrix, and best management practices. The framework itself classifies stressor receptor interactions and contains the overarching principles that guide the transfer of data. The data collection consistency table outlines parameters for comparison of data between projects, including preferred measurement methods or processes, reporting units, and most common methods of analysis or use of data. The monitoring datasets discoverability matrix catalogs relevant datasets in an online interactive tool that allows users to easily find and access data based on the approach presented in the framework. And we actually just released this matrix last month, which you can find on TETHIS at this URL to the right, so we encourage you to go check it out. The BMP suggests 4 practices to guide and implement data transfer. And these components all work together to achieve data transfer. And we vetted this process with regulators and the marine renewable energy community and incorporated feedback we heard throughout the different events and workshops that we held. And as I mentioned before, data transferability is a key aspect of risk retirement process, which you'll hear more about later today.
Thank you, Michaela, and good morning or good afternoon, everybody. So you were invited to this expert forum because we consider you are expert in the field, but we figured that it would be better to have a quick overview of what we consider change in habitat, so we are all on the same page. Next slide, Debbie, please. So for this brief overview, I will use this illustration from the chapter of the State of the Science report. It's a very hypothetical site where you have two wave energy converters, one on the surface, one on the seabed, on one tidal turbine, on all connected with cables to the shore. Next slide. So one of the first effects that could change the habitat that we see is during the installation with laying cables or setting devices on the seafloor, there is potential for impact on the benthos right in the path of the cables or under the devices themselves. Next slide. Another effect that we see is by adding hard structures like the devices themselves, the cables, the moorings to the water, and especially on the seafloor. There is potential for change in flow around the structure that would create some scour effect around the base, with a potential effect of changing the sediment on the communities therein. Next slide. And so this addition of hard structure can have some indirect effect, like that are more expected at a larger scale, which would be change in nutrient on the plankton dynamics, so phytoplankton or zooplankton dynamics, and that could succeed into changes in the food web dynamics. So, but those effects are not expected at a small scale of 1 or 2 devices like we are talking today. Another effect is a very natural process, the colonization of the devices themselves by sessile organisms. For engineers, this is usually known as biofouling and considered usually negative, but it's a very natural process. However, an indirect effect of biofouling could be the facilitation for installation or dispersion of non-native species. Next slide. A subsequent effect of the colonization is that the devices or cables can act as artificial reef or fish aggregating device. Often fish are attracted to artificial structure for additional new shelter or food. And we've seen that effect also with motile organisms like crabs. Next slide. And so the colonization, the artificial reef, all these effects can lead to changes in communities on the devices themselves, in the surrounding habitats, either on the sediment or in the sediment, or even the water column around. And those have indirect effects. Thank you, Debbie. Those indirect effects are seen more at expected more at a larger scale. So those are effects like the reserve effect, when the area around devices are close to fishing activities. So fish and other targeted species benefit from the protection in the device area, and they could lead to some spillover to the non-protected area if they move out. And we could also see some indirect effect on the food web with additional biomass or feces or predation in the device area. And so in the next several slides, Debbie will show you I will start, then Debbie will show you the evidence base that we have gathered for change in habitat. We really selected a few studies to present, because if we were presenting them all, we would be here for hours. But we've split the categories we want to talk about into learning from surrogate industries, then the effects of the installation or removal of devices on the benthos, then the changes in community composition that we can see on or around devices, and then the artificial reef effect. You see the three icons on the bottom. You will see them throughout the evidence base. The first on the left shows the surrogate industries. Then we have wave energy studies, and then tidal energy studies. Next slide, thank you. And so what do we mean by surrogate industries? I imagine you are all very familiar with that, but I wanted to remind you that we can learn a lot from other industries that have been in the water and the ocean for many years, if not decades. One that we have learned a lot from is the offshore wind industry, with turbines either bottom mounted or floating. They can have effects that are very similar to what is known or expected from wave and tidal devices. We can also learn a lot from fish aggregating devices, boat wrecks, oil and gas platforms, power and communication cables on the seafloor, oceanographic buoys. All these industries have part of their components that are similar to what a wave or tidal device is, or similar effects. And so we've been learning a lot already from these industries, and we expect to still keep learning throughout the next years. And so each, at the end of each presentation for categories today, we'll show you a summary statement, and I will ask you to use poll everywhere to tell us how much you agree with that statement. So for the surrogate industries, our statement is that structures in the marine environment have been studied for many years, even decades, and we know a lot about these processes already. So with some thought given to specific applications, data collected in other industries like offshore wind can be relevant to marine renewable energy.
Great, thanks, Leneg. So in this next segment of slides, as Leneg mentioned, I'm going to present results from some key studies that fit into each of those three categories that Leneg introduced, and provide examples of what we already know about the effects of habitat change. Each slide is focusing on a key study or project. And as Leneg mentioned, for effects of device installation / removal on the benthos, we're primarily considering habitat alteration from installation of a device at the footprint. So this first study was completed at the Seabed tidal turbine in Northern Ireland. Diver video surveys were completed before and at multiple times after installation. Analysis of the video collected showed that approximately 50% of the visible surface area of the device had been colonized, which fully replaced the area that was disturbed or removed by the device installation. Given the level of colonization of the device within 2 years of installation, it was anticipated that after decommissioning, the benthic community would recover rapidly to a state similar to baseline conditions. This next study at PacWave-North in the United States looked at the effects of anchor installation and removal on the sediment and macrofauna at the site. And we'll hear a little bit more about this in one of our examples later, but I just wanted to briefly overview the findings here. The anchors shown in the image were deployed with a monitoring buoy at the site, but they're very similar to what would be used in a wave energy converter deployment. Box core samples were collected around anchors in use, after removal, and at reference locations to compare the sediment and macrofaunal composition. No significant differences in sediment mean grain size and macrofaunal communities were observed between the study sites at anchors and at the reference sites. And again, we'll hear more about this in a little bit. So this literature review of cable impacts from multiple industries, including tidal, reported overall low impacts on the benthos from cable installation and removal. Most of these impacts are positive, such as adding hard substrate for colonizers. In one study included in this review, with cables that were laid in a jetted trench, diver surveys found that the cable route was undetectable 1 year after installation. With respect to other human activities at sea, physical disturbance to the seabed from cables is very spatially limited. Due to the small spatial footprint of cabling, the overall impact on benthic communities can be considered negligible, especially if unique habitats are avoided. So as Lindig mentioned, for each of these categories, we're providing that summary statement for the effects of habitat change with the intention of guiding us towards risk retirement. These studies and other key studies of effects of device installation and removal show that for small numbers of devices, there may be a net positive or neutral effect from installation of underwater structures on the benthos. If properly cited, negative effects are minimal. All right, the next category of effects is changes in community composition on and near devices. Here we're focusing on changes after installation to the device and the area around the device relative to natural variability. So for this first study, marine surveys were undertaken at 10 locations around the Orkney Archipelago to assess the biodiversity of submerged marine fouling communities. Surveys were conducted at harbors and marinas throughout the archipelago where MRE deployment and service vessels operate. In addition, several structures associated with the marine renewable energy industry were evaluated at EMEC test areas during this same period. Wave rider buoys at multiple locations, shown in the photo on the left, and a mounted acoustic Doppler current profiler at the Fall of Ornis, shown on the lower photo on the left. Analysis of the biofouling community data identified significant differences in fouling communities between harbors and marinas and marine renewable energy infrastructure. Key species identified as responsible for these differences were identified as Chirona haemeri, which was on a tidal mooring, Ova lactuca on wave rider buoys, and Semibalanus balanoides on the harbor wall. During this study, 6 non-native species were identified at harbors and marinas, but none were recorded at wave and tidal energies testing sites. The study shows that while key biofouling species are present in harbors and marinas, where MRE devices will be serviced, these species were not transported to the device environments. These findings suggest that MRE devices will likely be colonized by species already present in the surrounding community at the deployment location, not by new fouling species or non-native species. The next study is at the Seabed tidal turbine, same study as before. They also reviewed some more long-term impacts on community composition. Those diver video surveys completed before and at multiple times after installation found that observed changes in the benthic community were consistent with changes at the neighboring reference station, suggesting that any changes were well within natural variability. This study from the deployment of the open hydro tidal device at EMEC looked at benthic changes over time. Commercial fishing and towed video camera techniques were used over 3 sampling periods in 2009 and 2010. Compared to a control site, the benthos at the device site had increased species richness, biodiversity, which is shown in the graph, and significantly different community composition. This was primarily due to higher numbers of predators, including crab and lobster. While these results clearly show effects from habitat change, the impact was not considered negative by the report authors. This study carried out video camera surveys after 2, 4, and 5 years after cable and rock armoring were installed at Wave Hub in the United Kingdom. The study found that epibenthic assemblage composition and number of taxa were significantly different along the cable compared to the control sites, but that abundance was similar in all survey years between the cable and controls. The cables covered 0.01% of the surrounding bioregion and appeared to be supporting similar assemblages to the surrounding habitat, and they exhibited minimal evidence of invasive species, containing 3 records of 2 non-native species. This suggests relatively minimal impacts of cable presence on benthic community composition in the area. This study at Lysekil Wave Park in Sweden looked at the effects of device foundation presence on a soft bottom habitat predominantly occupied by polychaetes, echinoderms, and crustaceans. Macrofauna biomass, density, species richness, and biodiversity were higher at the research site, shown in black on the graphs, than at the neighboring reference site, shown in gray. This increase in colonization varies greatly over the years due to the dynamic nature of the environment. The deployment of wave energy converters at this research site tends to have relatively minor effects on the benthic community relative to the natural variability at the site. So these studies and other key studies show that hard structures in the water column or on the surface will become colonized, and benthic communities in the near vicinity of a device may change, but these changes are considered neutral unless they facilitate colonization of non-native invasive species. All right, the next and final category is artificial reef effect, which looks at how mobile organisms respond and may be attracted to the new habitat created by device installation and colonization. This study at the Open Hydro Tidal device deployed at EMEC used video footage and acoustic Doppler current profiler surveys to examine fish presence and water velocity around an operational device. Pollock were observed shoaling around the device periodically with abundance associated with the velocity rate. Fish were potentially using the device for temporary protection from currents and feeding. This study at Lysical Wave Park used diver surveys over multiple years to identify presence of fish, crab, lobster, and to assess the impact of wave power foundations on mobile organism presence. In both survey years, higher average abundances and more fish species were noted on foundations than in the controls, although this was not statistically significant due to sample sizes. This literature review provided a comprehensive look at comparable devices that could act as surrogates for MRE devices to understand potential artificial reefing effects, specifically across the United States West Coast and in Hawaii. The review finds that wave and tidal devices placed on or near the seabed in coastal waters of the US West Coast and Hawaii likely will function as small-scale artificial reefs and attract potentially high densities of reef-associated fishes, and that water column and surface expression of devices in Hawaii will function essentially as a fish aggregating device, with species assemblages varying by distance to the shore and depth. The results of the review also indicated that some of the previously postulated negative effects of wave energy structures on special status fish species, such as increased predation of juvenile salmonids or rockfishes, are not likely. So these studies and other key studies show that MRE devices display the same artificial reef effects as other industries. Impacts are likely to be neutral or result in a positive effect on species abundance. All right, so that concludes the presentation of these just few select studies from the habitat change evidence base that we have compiled. Many other studies have been considered, but obviously we don't have unlimited time today. We will send you this link in a follow-up email later this week, and that's where you can find the complete list of studies included in the evidence base for habitat change. So at this point, we are going to hear from two guest experts to speak about their experience working with regulators on marine renewable energy projects focusing on habitat change. Jennifer Fox from Aquaterra and Orjip Ocean Energy will be presenting some case studies from Scotland, and Sarah Henkel from Oregon State University will be presenting an example from PacWave in the United States. So at this point, I'll hand it over to Jen.
Brilliant. Well, firstly, thanks for that really comprehensive introduction to the topic. I think we're going to have some interesting conversations in the discussion breakout groups afterwards, judging by the chat so far. So great to see that. Yeah, and thanks for that introduction. So I'm going to very briefly, and I will try to be brief, go through some examples from Scotland specifically, and try to put what you've presented so far in a context of real consenting examples in Scotland. Next slide, please. So what I'm going to present firstly is the way that the details of habitat change, as you guys have presented, are assessed within real tidal energy examples. The examples I've used in this presentation are the Brims project and the Maygen project, which I'll explain a little bit more in a second. So going through how key impacts were assessed, how cumulative impacts were assessed for those projects, and some mitigation measures and key conclusions there. I do have some additional examples on habitat change in post-consent monitoring, and those are some examples from EMEC, which is the Marine Energy Test Centre here in Orkney. I'll keep an eye on my time, and I can drop that and bring it up in the discussion sessions if I run over my time. So next slide, please. So I'm sure everyone in this group is quite familiar with the Maygen project, but I just wanted to provide a very brief overview, just in case anyone wasn't familiar. Maygen is where this red arrow on the bottom left of your screen is, right in the north coast of Scotland in the Pentland Firth. And the EIA for this project was completed back in 2014. The project, as you may well know, was sought to be consented in 2 phases. So the EIA that I'm talking about today was the consent for phase 1 of the project, which is an 86 megawatt project. Next slide, please. And I'm also going to talk about Brims, which is a project that might be slightly less familiar to those of you on the call today. This is in not a dissimilar area to that of Maygen. This is the north coast of Scotland that we're looking at in the Orkney Islands, which is where I am at the moment. And if you see the red box on that map, that's the agreement for lease area for the Brims site, which is off the south coast of an island, the island of Hoy here in Orkney. That EIA was submitted in 2016. Unfortunately, Open Hydro went into administration, and so the consent wasn't completed. But through extensive consultation with the regulators here in Scotland, all the indications were very positive that it could be a project that could be consented, and the EIA was completed and submitted to Marine Scotland, the regulator. And that was a full EIA done for the full capacity of the project, which was 200 megawatts. Next slide, please. Again, I'm sure many of you are quite familiar with the environmental impact assessment process, but I just wanted to put some brief information here for any of you who don't work in the consenting process day to day, just to outline what it is that goes into an environmental impact assessment. And apologies, you're probably not going to be able to read this flowchart on the left-hand side of your screen. This is taken from Marine Scotland, who's the regulator in Scotland, and it just outlines the process of a screening of the potential impacts of a project, which leads to a scoping phase, which looks at any likely significant effects of a project, or those that can be scoped out if there are no likely significant effects of a project. That then goes into a detailed and extensive consultation phase with statutory and non-statutory stakeholders, which all feeds into the to consideration within the assessment of impacts, and ultimately that is all compiled into an environmental impact assessment report. And on the right-hand side here, I've just pulled these from the Maygen is the colourful one on the top, and from the Brims project on the bottom. This is just an outline of how these impact assessments are summarised to ultimately deduce significance in these impacts. So a detailed look at both the magnitude of the impact and the sensitivity of the receptor can lead to the conclusion on the significance of the consequence of that impact, and ultimately the significance of the effect itself. The next slide, please. So I'm going to go into a little bit more detail on, I think it's 4 of the impacts that you guys have already presented, and how these were dealt with in both Brims and Maygen. I haven't split these out into these 2 projects specifically. What I've done is I've looked at how they were dealt with in both of the projects, and I've tried to condense and just present the key summary of how these impacts were dealt with in both of the projects. So the first one to look at here is the direct physical impact or loss of habitat, and how the impact pathway is presented for both of these projects is that firstly, any sessile species in the direct area will be damaged or destroyed, and any mobile species will be caused to move away. And some of the mitigating factors, or I suppose variables to consider as part of the assessment was that in both of these areas, and very much by design, there were no species of specific conservation significance present, and that was deduced through existing literature, existing data that was available, and additional baseline surveys that were conducted on the benthic environment. No large aggregations of animals were noted in these two areas, and it was also noted that damage during the installation phase of the project would be temporary. A key consideration for these areas were that there was quite a lot of kelp habitat in both of these sites. Kelp is a priority marine feature for Scotland, which means that while it's not legally a designated site as part of the Natura 2000 network, it is the list of priority marine features has been devised by the Joint Nature Conservation Committee and Scottish Natural Heritage. And these habitats and species do require additional consideration if there is predicted to be damage, disturbance, or removal of those habitats or species. And so this was a key consideration in the assessment of this impact. It was deduced that specifically for Maygen, at least less than 4% of the kelp in the area, and for Brims as well, it was a very small proportion of the kelp in the area that would be removed as part of the site area itself and the cable corridor, and thus it was concluded that while the sensitivity of the receptor was medium, the minor magnitude of the impact led the ultimate conclusion of the impact to be not significant. So next slide, please. The next one to have a look at is Seabed scour, which you've already mentioned. This was actually scoped out for the Maygen project. So what we're looking at here is a summary of how this was assessed for Brims. And as you've already presented, even minor changes to the benthic environment can have an overall effect on the species distribution in the habitat in general. So that is one of the reasons that the scour effect is a key consideration here. It's also noted that the scour effect is greater at cable route areas. As a mitigating factor of this, there was cable protection to be used. And it was also noted that there was a low level of sediment cover in the agreement for lease area in general. Additionally, it's noted that the installation vessels and maintenance vessels do cause this impact as well, but that this would be a temporary impact, and the spatial extent of that impact would be very minor and highly localized, and ultimately that was assessed as a minor significance impact as well. So next slide, please. The next one that was assessed as part of both the Brims and the Maygen projects was marine non-native species. So as we've already gone through, marine non-native species is something that is a risk in any project like this, where there are going to be hard structures brought in from sites outside of the local area, and also vessels that are brought in from sites outside of the area that may be carrying non-native species on the structures themselves or as part of ballast water. It's noted here that in general, most marine non-native species that would be introduced to a new area would not be viable due to the environmental conditions or the niche availability. However, where there are non-native species that do manage to get a hold and in a habitat, the risk to the native populations can be considerable and can cause a reduction in population numbers or a complete failure of a population as well. Part of this assessment was noting that the biotopes are not considered to be at risk of the introduction of marine non-natives. There was also mitigating factors introduced, such as local UK-based boats would be used, and that any hard structures to be introduced from a non-local area would be thoroughly cleaned before being installed as well. That added to the low level of conservation importance of the benthic habitats in the area, meant that the sensitivity was deemed to be medium. The bottom of my slide is getting cut off slightly. I'm not sure if that's happening for you guys too, but ultimately the magnitude of the impact was deemed to be minor and hence not significant. And next slide. Yeah, thank you. So the last one to consider here is the introduction of new hard structures, also can be thought of as colonization or the artificial reef effect. So what was considered as part of the assessments here was that the new habitat was the introduced habitat, or the hard structures, was similar to that existing rocky habitat in the area. And therefore the potential change in species composition would be limited. It was noted that there could be additional colonization from species that are not as common in the area, such as blue mussels, and that this would provide a food source for fish, echinoderms, and crustaceans. There would be anti-fouling measures used on the hard structures to limit this effect. Due to this and the low conservation significance, as I said, of the benthic habitats in the area, this impact was deemed to be not significant overall. So next slide, please. So as I said, I just wanted to also touch on cumulative impacts, as this is something that is challenging to do a cumulative impact assessment, and not quite as clear as to how in detail these kind of impact assessments are done. And so I wanted to just show, in the case of these two projects, how these impact assessments were done for these specific impacts that we're talking about today. So firstly, a list of projects were identified together with the regulators and key consultees for those two projects that would be happening in the region, in the general area of the Mitigation or Brims project, and the timelines of those projects were also an important consideration. This list of projects was agreed upon, as I say, by both the developer and the regulator, as well as key consultees, and thus were used as the basis for the cumulative impact assessment. For both projects, for the installation and construction and decommissioning phases of the project, the timing of those other projects in the area were not going to overlap with the timing of the installation, construction and decommissioning of either of these projects, and hence there was no cumulative impacts needed to be considered for those phases of the project. For the operation and maintenance phase of these two projects, the cumulative impact of loss of habitat and species were assessed, but ultimately due to the low diversity circulittoral tide-swept rocky communities dominated by sessile fauna and low conservation significance of these habitats and species, the overall effect was considered to be minor and therefore not significant. The marine non-native species was also considered to be an increased risk with the cumulative impact of more than one project. But again, the mitigation measures that I've already discussed, along with the standard guidelines of the use of vessels to minimize the risk of the introduction of marine non-native species, were considered to be appropriate to minimize this risk and ultimately conclude that it was a non-significant risk. So next slide, please. Yes, thank you. So again, I've talked a little bit about the mitigation measures, and I just wanted to focus on this specifically for a second, as this is a key part of why those impacts could be assessed in a relatively straightforward way and ultimately be concluded to be not significant. Firstly, in both of these projects, and as I'm sure many of you are familiar with, the Scottish Government is very supportive of the Survey, Deploy and Monitor strategy. So both of these projects have monitoring strategies in place that allows the regulator to be supportive in general of the deployment of projects where the risk can be minimized and monitoring plans can be put in place. As I said before, there were baseline surveys that were done to fully define what the habitat types were and the presence of species, and those included detailed cable route surveys to avoid sensitive habitats. The installation layout was clearly defined and communicated. That was specific to the example I gave on the kelp clearance area, to make sure that the numbers that were being used and the key routes of the cables were being defined so that that kelp clearance level could be analysed and assessed in a very detailed way. And the overall point I guess I'm trying to make with these mitigation measures is that these are standard mitigation measures that will be introduced in most projects, and for the most part that's what made the overall assessment of these impacts, as I say, relatively straightforward. So such as the next point I've got there, things such as far as is practicable, the depth and diameter of the turbine foundation piles would be minimized, non-toxic lubricants to be used in the structures themselves. As I said already, in relation to marine non-native species, all of the vessels would adhere to all relevant guidance, cable protection measures would be used, and standard anti-fouling coatings on turbines and the associated infrastructure would be used as well. Next slide, please. So just some key conclusions, and then I'm conscious of time, Debbie. I think I'm running way over my time, so I'll stop after this. But I just wanted to conclude with none of the impacts were assessed as significant. As I've said, those standard mitigation measures were employed as part of the impact assessment. And the key point probably is that that site selection was very deliberately done to avoid any species or habitats that might be of conservation importance or significance. And a key point in general for the EIA process, I think any one of us with experience in this area would know that early, regular and efficient communication with the regulator and with other key consultees is absolutely key to having any kind of success in this world of consenting. So I do have a couple more examples on EMEC, but I'll pause just there and check in with you guys because I'm conscious that I'm going over time.
Yeah, I think at this point we can move on to the next presentation. We will make these slides available along with the rest of the slides.
And I can circle back in the discussion if this is of specific interest to anyone. So I'll leave it there. Thank you very much.
Great. Thank you, Jen. All right, so at this point, I'm going to hand it over to Sarah Hankel from Oregon State University to talk a little bit more about PacWave.
Thank you. So go ahead and do the next slide. So again, to familiarize everyone with what we have going on here in Oregon. So we have two sites, which we call PacWave-North and PacWave-South. PacWave-North, we started the permitting process for in 2010, and we did have one very short test in 2012. It's our northern site. And it's 1 nautical square mile. And at this site, there's no permanent infrastructure in the water. We take out this test buoy, I think that was mentioned earlier, and wave energy devices can plug into our testing and analysis buoy for the duration of their test, and then everything is removed and at the end of the test. And so the consenting for that went more quickly. And we're nearly through the permitting process for PacWave-South, which the idea of that is it'll follow the model of EMEC, so it'll be a pre-permitted, accredited, grid-connected wave energy test facility. That one is 1 mile deep by 2 miles long, and within that there'll be 4 separate berths. Next slide. Oh, right, so there's our little test buoy. That's fine. Go ahead. And so for this site, our plan is to, you can see now the site is segmented into 4 slices, where within a berth, developers can test individual devices or arrays. We will have 5 subsea power and data cables, so 1 for each berth plus a backup. And then all of these will go to shore, and then to a shoreside utility connection and monitoring facility. So please click. And so here is our vision someday. This is now turned 90 degrees from how it's pictured in the ocean to make it fit on the slide. The idea is that 4 different developers could be potentially each testing small arrays. Okay, go ahead. And so the consenting process for this really mirrored the risk retirement pathway that was presented this morning, and I'll walk through that. But I think one of the first steps in that pathway is learning from surrogate industries. And so we first looked a lot into other offshore energy installations. Next slide. And anticipated that we would attract reef-associated organisms. I'm not sure what happened to my oil platforms. There were oil platforms behind those fishes. Looks like they got all real skinny somehow. And then we also looked at wind turbines and know that we expect shell mounds to form under them. And then one more click. And to expect to see scour occurring around the foundations. We see this both in oil platforms and wind turbines. And so these were the effects that we anticipated seeing around any installations we would put at PacWave-North or South. Next slide. So when, in 2012, we had the Wet-NZ device testing at PacWave-North, along with our Ocean Sentinel, which is the inset surface view you see there on the left. And we did ROV surveys of the anchors, which those anchors were shown earlier in the slide. You can see they are undercut. There's some scour around them. And then the other thing that was a little bit surprising was this white speckling that we saw all around the base of the anchors. So click again. And so starting in 2013, we collected box cores around these anchors in addition to the reference areas that we had been sampling. So click. And so one of the things that we noticed was this really significant accumulation of large gravel and shell hash, pictured there on the insets, around the anchors, and a little bit inshore of the anchors, and less so offshore. So what this plot is showing is over time from October 2013 through April 2016, and then you can see more on the left, the 30-meter reference site, 40 meters around the northeast anchor, and around the northwest anchor are grabs, and then 50 meters and 60 meters, which are more offshore. And so there was a substantial accumulation that did vary temporally of these large pieces of shell and gravel around primarily the northeast anchor. And this, I think there was a mention in the chat earlier of small sample sizes. So this is a single installation, and so we have 2 anchors to study, no replicates. So this is, but we seem to have found some sort of effect. So go ahead and click. As was mentioned earlier in the review of PacWave, we didn't find any statistically significant differences in the median grain size of the remaining sediment. So I would say, I didn't define that this residual proportion is what, when we do a box core and we sieve it, this is what doesn't make it through the 1 millimeter mesh. So what was left behind was not significantly different than before, but in some ways that wasn't surprising because this is a very medium to coarse sand site already, so there wasn't a lot of fine sediment to be scoured away. We didn't find any statistically significant differences in species abundance. When we did multivariate analyses, we didn't find any statistically significant differences. But we did potentially see an effect on richness. And again, this wasn't statistically significant because there's so much variability. But if these, this really hard to read plot on your screen, the 3 lines that have a longer time series are our reference areas, the 30, 40, and 50 meter reference areas. And then we see when the anchors go in, which are the blue and purple lines, around them, they actually started with lower species richness. Actually, all of the sites had this peak in species richness in early 2015. Even you can see there's red dots for the 30 meter site and beige triangles for the 40 meter site. So around the anchors, and then after this, whatever drove this peak in richness everywhere, later in the time series, the anchors again, their richness is lower than the reference areas. And so this is of course of sediment-based species, so kind of the opposite effect of talking about new species colonizing, but what was there before, right around the anchors, seemed to have lower species richness. So go ahead and click. So the PacWave permitting mirrored the risk assessment pathway, is that we looked at our project, found the stressors, which would be anchor installation, the receptors would be the sedimentary habitat or the animals there. So we defined the risk. We examined some existing data from oil platforms and wind turbines. We collected these data at PacWave-North from that one small installation, and then go ahead and click. What normally would have in the risk mitigation pathway would be maybe off ramps at stage gate 4 and 5. Instead, click again. What we did was in the approach for community or habitat change of the surrounding area, we applied an existing monitoring strategy, which is the box score surveys, to mitigate or accept the risk by quantifying changes and having check-ins to see if these changes were limited in magnitude or extent, then maybe that risk could be acceptable to the project. And then I didn't talk much about artificial reef, but we're testing a novel tool. In this case, we've got a new autonomous ROV that we're gonna attempt to use. And again, if this novel mitigation measure, this new tool can quantify the changes, then maybe this risk can be accepted. So go ahead and click. And so in our case for PacWave, the risk was mitigated by monitoring. So that's how we made the risk acceptable. Go ahead, that's fine. And so we have, just as in Scotland, a long list of pre and post construction monitoring and mitigation measures. And so there's 10 different categories here, and 2 of them are what we're talking about today, the benthic fauna and organism interactions, and then click. So the part of the mitigation measures are monitoring. And so for these 10 mitigation measures, 4 of them include a monitoring plan. And so for the benthic sediment and infauna, we think about the effects of installation and removal on the benthos and colonization and changes in community composition. And then our organism interactions is what we, within our project, are calling basically the artificial reef effect. So how are organisms interacting with the structure that's at the site. So go ahead and click. And so pictured here are our benthic and artificial reef monitoring tools. So our super old school box core that's been around since the 1970s, and then our new autonomous ROV. And so the inset there is just a picture of it attempting to autonomously survey a square without any human involvement. And it's pretty good on the on the perimeters, turning the corners. It has a little bit of challenges still. So click again. And so here is just a schematic of all of the places that we will box core and survey with ROVs in relation to the 4 different berths at the site. And every spring and late summer, these surveys will be conducted for the first 5 years of the project. The cable surveys may conclude after 2 years, and so our mitigation for this is to conduct these monitoring surveys and then check in with our adaptive management committee, which is made up of a number of different experts and regulators, to look at the results of this monitoring, see if it's effectively quantifying change, looking at the magnitude of that change, looking at the extent of the change, and then if that's, quote, acceptable, then the monitoring can come, we'll have an off-ramp for the monitoring. So click. So currently, very recently, in fact, Our project has received its FONSI, the finding of no significant impact. But this is, of course, due to the intensive monitoring that we have committed to in order to get our license. So that's it.
Great, thank you. And thank you so much, Sarah and Jen, for those excellent presentations. So now we'll discuss risk retirement for each category that we have talked about today in small groups. Debbie has already broken everyone up into 2 separate groups, and Andrea will be leading discussion in one of the groups, and Lene will be leading discussion in the other one. And we will end each breakout group with reporting out on the discussion, about 2 minutes for that report out for each group. So a really quick summary from those.
So we had a great discussion. We got bogged down on the first few questions, of course, so we rushed through some others. But I think at a very broad level, the big things that came out was the importance of scale, that much of what we know about benthic habitats and other habitat change, we don't have long enough records of what is actually going to happen. We only have short snapshots. We can take some of it from surrogate industries, but there are significant differences because of the high energy places that marine energy is placed. So having these longer term monitoring programs is really important. It was pointed out that we tend to lump wave and tidal together, and yet the locations they go into and the features of those are so very different. We should probably look at habitat changes separately for tidal and for wave, particularly as we start to scale up, because the tidal habitats tend to be in quite small, much smaller areas. So this becomes really quite significant. We need to be thinking about things like artificial reefs, not necessarily it's positive, it's negative, it's there, and what are the changes, not just in species diversity and abundance that are likely to happen, but if there are changes in this diversity, it's not just species, it's also functional places that those species have occupied in the community and the ecosystem. I think those were sort of the big high level ones. A little bit of discussion around decommissioning, because we've done so very little of it that we have to be rethinking what habitat has been created by these structures, and is ripping it all out the right approach across the board, or should we be thinking about whether we are actually changing fairly well long established habitats. So in no particular order, that's kind of what we talked about. Anyone in my group that I missed anything big?
You did pretty well, Andrea.
Thank you. Okay. All right. Any
So
questions, or do you want to go ahead, Lene?
No, I'll go ahead, summarize what we talked about in my group. We started with 7, we ended up with, we started with 8, ended up with 6. Like in your group, we got a very good discussion on the first couple of topics, especially what we can learn from surrogate industries. So the main point to take from that is that there is a lot of lessons that we can learn from them, but those surrogate industries tend to be in habitats actually quite different from those we are looking at. Especially there is no surrogate industries for high velocity tidal habitats, and so there is lessons that we can learn from those industries, but not much data that we can effectively transfer. We also discussed about the other risks. People in general in the group agreed that we could consider colonizations or artificial reef effects, risks that could be retired for small levels, small numbers of devices, but with the caveat of there needs to be guidelines on frameworks for monitoring, on characterizing those risks, those changes, especially in habitats where we don't know much yet, like tidal habitats. There was a discussion about biofouling, and that we could learn from biofouling in offshore or offshore wind or oil and gas. But species could be different in a high energy environment like tidal or wave. But there could be, there may not be as much non-native species settling there due to the high hydrodynamic and the biogeographic barriers.
We are planning a webinar broadly on risk retirement in September. We've done a couple of these, but for very specific groups, including regulators only. So we will be doing that in September, and you'll all get a notice of that, which will delve into that lovely little drawing in even more gory detail. The next steps we're taking, we've been playing with these evidence bases, but we recognize that to make them useful to the regulatory community, we really have to put them more in that context. So we are writing a series of guidance documents. This is through Ocean Energy Systems Environmental. We'll write some guidance on how the science we have can be sort of directed towards the major regulatory consenting buckets, sort of, is this about species? Is it habitats? Is it water quality? And looking at those in a way that we hope will be more accessible to regulators. We will do this on a somewhat generic basis and then engage the countries involved in OES-Environmental to make them more specific to their country's regulatory processes. And finally, we are, in fact, working on a white paper to look at risk retirement for oceanographic changes. This one's a little bit different because, of course, it's all associated with numerical models. And doing the same sort of thing we've done here today didn't seem very productive to us, mainly because it will be dueling models. Everybody has the best model, of course. So we will be bringing a white paper out and circulating that around, trying to get input. So if you have colleagues with an interest there, let them know that'll be coming, and we'd love to engage them in discussion around that. So that's kind of where we are and what we're doing. And I think that's it, unless anyone has any closing remarks. I'd just like to thank you again for all your time, and particularly give kudos to my team here, Michaela, Leneg, and Debbie, who really got all this done. So thanks very much.